separation processes. In the previous two lectures, we got introduced to the basic aspects of design of the separation process module or separation process systems of a chemical process, and thereafter we had some discussion on the design aspect of design aspects of distillation column, which is the most popular or most frequently used separation process in most of the process industries. In this lecture, we shall go ahead and see the design of distillation column, the aspects of exact design of distillation column. There are two basic approaches used in design of distillation column. First is the design and second is the rating. The former approach involves design of a new column to determine the column diameter and height required to achieve specific separation, while the rating approach involves retrofit an existing column in which the column diameter and height are already fixed and the flow capacity and separation are to be determined. Means fitting of an existing column for another purpose other than what it was designed for. There are two types of distillation columns. First is the packed distillation column and second is plate distillation column. You have learned the basic aspects of these columns in the NPTEL course of mass transfer. Today we shall see some practical aspects of these columns and also some practical design procedures than what you have learned in mass transfer operation course of NPTEL. Let us start with the design procedure of a column with sieve trays. Sieve trays are the most popular columns, column internals that are used. The first step in the design procedure is to establish the composition and physical properties of the feed and the products, that is the overall mass balance across a distillation column. The feed rate and any additional limitation also has to be determined. Limitation could be such as the maximum temperature and pressure drop limitation or presence of some corrosive or toxic component in the feed which has to be removed in priority to others. Mass transfer operations course of NPTEL, you have mostly dealt with binary mixtures, but in industry you will rarely find a binary mixture to be distilled. The mixtures that are encountered in industry are multi-component mixtures with more than 5, 6 or maybe even 20, 30 components. Okay. So, we need a different approach, although the basic principle remains the same, we need a different approach for design of columns for this multi-component separation, okay, and that is what is going to be today's discussion. The second aspect of the second step in the design of column with sieve trays is that of the selection of design variable. Operating pressure is the first variable to be addressed. In the previous lecture, I showed you some aspects of design of distillation columns in which operating pressure variation can give flexibility in terms of energy integration, okay, that thermally coupled columns and all those things we have seen in previous lecture. Increase in operating pressure results in increase in the separation difficulty because alpha, the relative volatility decreases, increase in the reboiler and condenser temperature, increase in the vapor density and decrease in the latent heat of vaporization. The lower limit is set by the desire to avoid vacuum operation and the use of external refrigeration for condenser to avoid rise in the operating cost. As I told you in previous lecture, if you increase the pressure of a column, then reboiler temperature increases, condenser temperature increases, and if you reduce the pressure of a column, then both of these temperatures decrease. Okay. Now, we want to set an optimum pressure in such a way that we can use cooling water, which is the cheapest utility for operating the condenser of the distillation column, and we can use either a medium or high pressure steam for operating the reboiler. If the process constraints permit, the pressure is so set that the cooling water and air cooling can be used in condenser. Okay. That is, the bubble point of the overhead product is at least 5 to 10 degrees above the summer cooling temperature. The second variable that needs to be set is the reflux ratio. You have seen the variation of the column plates with reflux ratio in the course of mass transfer. You know that with increase in the reflux ratio from its minimum, the capital cost will be reduced because the number of plates will reduce. However, the utility cost will go up because more reboiling will be required, more condensation will be required, and if the capital cost involved in the separation process is annualized and combined with the annual cost of utilities, you will always find that the total cost passes through a minimum against a reflux ratio. Most designers use the optimum reflux ratio as 1.2 times the minimum reflux ratio. This is a thumb rule of distillation column design. Another design variable which may be of relatively lesser importance is the vapor liquid condition of the feed. Again, in mass transfer operations course, you have learnt this particular aspect of distillation. In that course, you have defined a Q line, which is quality line, and Q represents the quality of the feed. For Q equal to 1, the feed is a saturated liquid, and for Q equal to 0, the feed is saturated vapor. But for other than 0 and 1 values, if the feed is subcooled, then the number of trays in the rectification section decrease and the number of trays in the stripping section increase, and this feed condition requires more heat in the reboiler and less cooling in the condenser. And if the feed is superheated vapor, then reverse happens. Okay. Establishment of the physical equilibrium data is the next step in the distillation column design. Physical equilibrium data means basically the VLE data, vapor liquid equilibrium data. Either experimental or modeled phase equilibrium data reported in the literature or self generated data can be used. Nowadays, there is tremendous database available in the literature. So, for practically any mixture, you will have the data already reported in literature. You have to look through proper sources. Okay. But most of the data that is reported in the journals and handbooks is for binary mixture and not for multi-component mixture, and therefore, it is necessary to combine this data with a model to predict the multi-component behavior. Several models are available in the literature like Wilson model, NRTL model, UniQuack model, universal quasi-chemical, and UniFac model, which is the most rigorous approach. If the binary data is not available, you can use this model for prediction based on the functional groups that are present in the compounds to be separated. Then comes the aspect of determination of number of equilibrium stages. In mass transfer course of NPTEL, you have learnt the McCabe-Thiele method or Panchon-Severett method for determination of the theoretical number of equilibrium stages, but this is mostly for binary mixtures. How do we use the same method for multi-component mixture? Of course, the approach has to be changed. Okay. It has to be more rigorous, and there are several shortcut methods that are reported in literature for determination of number of theoretical stages for separation of multi-component mixture. We shall see in today's lecture two popular methods that are used for this purpose. The first method is FUG method, Fenske, Underwood, Gilliland method, and second method is the smoker method, which is essentially the analytical approach to the McCabe-Thiele method, which is a graphical solution. Let us first see the Fenske, Underwood, Gilliland method. To determine the number of equilibrium stages, the minimum number of stages and minimum reflux ratio is required. The minimum number of stages n minimum can be obtained from Fenske's equation. N minimum is equal to ln into x Lk divided by x Hk distillate into x Hk by x Lk bottoms divided by ln the log of alpha relative volatility between light key, that is Lk, and heavy key Hk component. Exactly same expression you have derived in mass transfer operations course for binary mixture. Okay. In that case, you had defined Xd and Xb, where you had only one, when you had two components, one more volatile and other less volatile, then Xd by Xw, the mole fraction of more volatile component in distillate divided by Xw, the composition of more volatile component in bottoms. Exactly same thing is here, but we are now defining Lk and Hk components, which is light key component and heavy key components. This is for multi-component mixture. Suppose we have a mixture of 5, 6 or 10 components, then we mark one component as light key component, which is among the lower boiling range, and one component as heavy key component, which is in the higher boiling range. And this expression that appears on the screen is exact analog of the binary expression that you have learnt in mass transfer operation for multi-component mixture. Okay. Now, here in the denominator we have used the average value of alpha, relative volatility. Now, why? Because in case of multi-component mixture, the relative volatility between components may sometimes change with temperature. It may also change sometimes with the composition, okay, as the separation proceeds, and therefore, we have to use an average value, average of the minima and maxima of the relative volatility. Okay. So, usually the volatility is not mathematically or numerically algebraically averaged, but it is the geometric mean that is taken, that is alpha Lk by Lk average is alpha Lk at bottoms, that is relative volatility between light K and heavy K component in the bottom at the highest temperature, and alpha Lk at distillate, that is the relative volatility at distillate, which is lowest temperature in the column, raised to half. This is the geometric mean of the two volatilities. After we have determined the minimum number of stages, then we have to determine the minimum reflux ratio. For that purpose, we have to solve two equations which are given by Underwood. The first equation is summation I running from 1 to n, where n is the number of components in the mixture, alpha I into xf I. Alpha I is the relative volatility of any component I with respect to heavy key component. Xf I is the composition or mole fraction of that component I in the feed. Alpha I into xf I divided by alpha I minus theta is equal to 1 minus q. This q is again the quality factor that we have seen earlier. Q equal to 1 implies feed being at saturated liquid condition, q equal to 0 implies feed at saturated vapor condition. Theta is a intermediate, is a basically mathematical parameter which has to be determined. Now, if you have a multi-component mixture and if you write down this summation and simplify, you will get a polynomial, and roots of those polynomials are the values of theta. You will get n minus 1 values of theta for n components, but you have to take only that value of theta for the second equation, which is r minimum plus 1 is equal to summation I running from 1 to n alpha I into x di. Now, x di is the mole fraction of component I in the distillate divided by alpha I minus theta. So, solve the first equation, get all the values of theta and take only that value of theta which is between the relative volatility of light key and heavy key component, and then use that value of theta in the next expression and solve for R minimum. XDI is the mole fraction of component I in the distillate, okay, and that can be determined from the minimum number of plates. Okay. Distillate and bottom distribution of the non-key components in the feed can be evaluated after calculation of minimum number of stages, but minimum number of stages again are determined by Fenske's equation. So, the simple relation is XDI divided by XBI is equal to alpha I raised to n minimum, alpha I average raised to n minimum into XHK in the distillate and XHK in the bottom. That is the simplest, very simple relation between the composition of a component in distillate and composition of the same component in the bottoms. Then after determination of R minimum and N minimum, we have to calculate the actual number of plates, but now remember actual number of theoretical plates, not the actual number of actual plates or practical plates. Gilliland has presented a plot that related the quantity n minus n minimum divided by n plus 1 to the quantity r minus r minimum divided by r plus 1, okay, and the relation is later on transformed into an expression as a correlation essentially by Edgely, and the correlation reads n minus n minimum divided by n plus 1 is equal to 0.75 into 1 minus r minimum divided by r plus 1 raised to 0.566. So, after determination of n minimum from Fenske's equation, after determination of r minimum from Underwood's equation, you have to set r, which you can set as r equal to 1.2 times r minimum, and then determine the number of plates n. So, this is a very simple procedure, although it is implicit because you have to solve two polynomial equations to get the roots which are essentially values of theta, but you can easily program this and then get the number of plates that are required for a particular separation. We shall see another approach to determination of number of equilibrium plates. This is essentially analytical solution of McCabe-Healy method that you have seen in mass transfer operations course of NPTEL. This solution was given by Smoker, a scientist in US, and we shall see now the derivation of this method, that is the number of trays in the rectification and stripping section of a distillation column. For an ideal or nearly ideal binary mixture, the vapor liquid relationship can be represented by Raoult's law over a wide range of concentration range. This you have seen in mass transfer operation course. Alpha is equal to y divided by 1 minus y divided by x divided by 1 minus x, okay, and this can be rearranged as y is equal to alpha x divided by 1 plus alpha minus 1 into x. Now, we had talked of variation in alpha sometimes because we had taken in earlier expressions average value of alpha, but in many situations when the molecules are not very chemically different or when the temperature variation across a column is not very high, in that case we can neglect the variation in alpha with temperature, assuming that the binary mixture to be a close boiling mixture of typically of hydrocarbons, or you can use value of average alpha also, that is also possible. Okay. Now, the VLE curve given by the Raoult's law is represented as follows. The diagram now appears on your screen. Okay. The VLE curve is essentially a parabolic curve, okay, and then we have to plot the two operating lines, one for the rectification section and another for the stripping section. Okay. Rectification operating line is above the feed plate and stripping line is below the feed plate. Now, let us say that we give a general expression for this operating line as y is equal to mx plus b, and then we plot specific points on operating line and the corresponding points on the vapor liquid equilibrium curve. X0 y0 as you see on the screen is the point on operating line, and x1 y0 is the corresponding point on the VLE curve. Then x1 y1 is the next point on the operating line, x2 y1 is the corresponding point on VLE curve, and so on and so forth. Now, if we eliminate y between equation 1 and 2, equation 1 being the Raoult's law and equation 2 being the general equation of a line y equal to mx plus b, then you get a quadratic expression in x, that is m into alpha minus 1 in x square plus m plus b into alpha minus 1 minus alpha into x plus b equal to 0. Now, you can very easily work out this. So, I leave this as exercise. This is equation 3. Quadratic equation will yield in two values of x. For any problem of significance in distillation, one and only one root of the above equation will lie between 0 and 1. Since x is a mole fraction, its value has two bounds 0 and 1. If the number is negative below 0, then that is absurd. If the number is above 1, then also it is absurd. We represent the root between 0 and 1 as k for that quadratic equation x equal to k, and then y corresponding y becomes mk plus b, and these values of x and y are the coordinates of the point of intersection of the VLE curve and the operating line, which is essentially this point, which now appears on your screen, this point. If we shift the origin of coordinates from x equal to y equal to 0 to this point of intersection between the operating line and the VLE curve, then we are exactly addressing the rectification section. Okay. We are no more take into consideration the stripping section, and then the coordinates of that point, that shifted origin, are x dash equal to x minus k and y dash equal to y minus m k plus b. And if you substitute these x dash and y dash, the new coordinates of origin, into the equation of operating line and the Raoult's law equation, then operating line equation becomes y dash is equal to m x dash, VLE curve becomes y dash is equal to y dash plus m k plus b is equal to alpha into x dash plus k divided by 1 plus alpha minus 1 into x dash plus k. And for x dash y dash equal to 0, okay, when we assume that particular point of intersection as the 0 point, origin point, then equation 9, which is the VLE curve equation, becomes m k plus b is equal to alpha k divided by 1 plus alpha minus 1 into k. And if we eliminate b from equation 9 and 10, okay, VLE curve and the VLE curve when x dash y dash equal to 0, then we get y dash is equal to alpha x dash divided by 1 plus alpha minus 1 k square plus alpha minus 1 into 1 plus alpha minus 1 k into x dash. Eliminating b, that means we are not considering the intercept anymore of the, so that we are considering just the VLE curve and the operating line which ends at origin. So, b is 0 essentially. We substitute a new variable c for 1 plus alpha minus 1 into k, which is appearing 2 times in the denominator, so that the expression becomes handy, easy to write, and then y dash is equal to alpha into x dash divided by c square plus c into alpha minus 1 into x dash. This is our equation 13. Equation 13 represents the Raoult's law expressed in coordinates determined by the intersection of the original Raoult's law equation and any operating line. We make this expression, equation 13, explicit in terms of x dash. So, just simple rearrangement, x dash is equal to c square into y dash divided by alpha minus c into alpha minus 1 into y dash. x0 dash y0 dash in the figure that I had shown initially represented any point on the operating line y dash is equal to m x dash. If we stepwise start the procedure of McApthilly method, that means we assume x0 dash y0 dash as the point representing the distillate of the distillation column. Okay. Then we get corresponding points, as I earlier mentioned, that x0 dash y0 dash extended horizontally to equilibrium curve will give x1 dash y0 dash, then that point projected downwards, perpendicular downward to operating line will give x1 dash y1 dash, and then x1 dash y1 dash projected horizontally to equilibrium curve will give x2 dash y1 dash, and so on and so forth. The coordinates of the point on operating line are related by equation 8, and those on the VLE curve are related by equation 14. Okay. Equation 14 is the VLE curve in shifted coordinates, and equation 8 was the operating line in terms of shifted coordinates, y dash equal to m x dash, but after setting b equal to 0, that means after shift of origin. And then follows a stepwise method. First, y0 dash equal to m x0 dash, x1 dash is equal to c square into y0 dash divided by alpha minus c into alpha minus 1 y0 dash. Now, eliminating y0 dash between the above two equation 15 and 16 expresses x1 dash in terms of x0 dash. x1 dash is the composition of liquid on the first plate, and x0 dash is the composition of the liquid which is being obtained as distillate. It is the same as y1 dash, okay, because the same vapors condense, but x1 dash is different. Now, why have we made the calculation in terms of x and not y? Because it is very easy to measure the composition of liquid. For example, if you are doing a simple experiment of benzene toluene distillation, the refractive index of the mixture changes with composition, and with simple measurement of just refractive index, you can measure, you can determine the composition of the liquid, and that is why we have made all our calculation explicit in terms of x and not y. Determination of composition of vapor requires special techniques such as gas chromatograph or liquid chromatograph, basically gas chromatograph, and then that is more tedious, but measurement of the composition of liquid is much easier. Okay. So, we proceed next point, y 1 dash is equal to m x 1 dash, and then corresponding point on the VLE curve x 2 dash is equal to c square y 1 dash divided by alpha minus c into alpha minus 1 into y 1 dash. This you can rearrange by writing y 1 dash in terms of x 1 dash. So, m c square x 1 dash divided by alpha minus m c into alpha minus 1 into x 1 dash, and now x 1 dash you can write in terms of x 0 dash here. Okay, eliminating x 1 dash from equation 17 and 19 expresses x 2 dash in terms of x 0 dash. So, x 2 dash is equal to m square c raised to 4 x 0 dash divided by alpha square minus m c into alpha minus 1 into alpha plus m c square into x 0 dash. And if you proceed stepwise like this, then you can write expression for x 3 dash. Now, this is a big expression, but obtaining it is rather straightforward. You have to first get x 3 dash in terms of y 3 dash, and then substitute for y 3 dash, and then substitute for x 3 dash in terms of x 2 dash, x 2 dash in terms of x 1 dash, like that. Okay. So, generalizing this stepwise procedure, we can obtain a general equation as x n dash is equal to m raised to n c raised to 2 n into x 0 dash divided by alpha raised to n minus m into c into alpha minus 1 into the bracket alpha raised to n minus m raised to n c raised to 2 n divided by alpha minus m c square into x 0 dash. You can rearrange expression 22, I am leaving this as homework as I have written here, left as homework. So, you can take log on both sides and then rearrange this equation explicit in terms of n. So, n is equal to log x 0 dash divided by x n dash into bracket 1 minus m c alpha minus 1 into x n dash divided by alpha minus 1 alpha minus m c square divided by 1 minus m c alpha minus 1 divided by alpha minus m c square into x 0 dash, and the whole numerator divided by log alpha divided by m c square. This equation is an accurate analytical expression for the number of plates, number of theoretical plates, okay, represented by concentrations x 0 dash and x n dash, the operating line y is equal to m x, and the vapor liquid equilibrium curve characterized by alpha. Now, what is the beauty of this expression? We have already learnt calculation of or determination of the equation of the operating line in the course of mass transfer operations of NPTEL. For example, the equation of the operating line of the rectification section is equal to y is equal to r divided by r plus 1 into x plus x d, which is the composition of more volatile component in distillate, divided by r plus 1. So, if we want to fit the y is equal to m x plus b kind of expression to this, then m, which is the slope of operating line, is equal to r divided by r plus 1, and b, which is the intercept of the operating line, is x d divided by r plus 1. Simply by substituting these values here for a given separation, that means what should be value of x 0 what should be value of x 0, which is essentially x d, and x n here, remember, is the feed plate. This expression was solved for only half of the total McApthily diagram. How did we do this? By taking the intercept to be 0, because we shifted our origin to the point of intersection of the operating line and the equilibrium curve. So, in a McApthily diagram, which typically looks like this is y equal to x line, diagonal line, this is a VLE curve, and then you start calculations from given x d and given x b, and then you make out number of plates, Okay. So, we have considered only this portion, the portion which I am now hatching in red. Okay. Only we have considered only this portion, because we considered the cross section or the point of intersection of the VLE curve and the operating line as our last point, as our origin. So, we have determined the number of plates in the upper section of the column. This point is essentially the feed point. Okay. So, we have determined the number of plates in the rectification section. You can apply exactly the same expression for the lower section of the column, the stripping section. However, you have to be careful about values of m and b. Here you have learnt the determination of equation of operating line for the stripping section in course of mass transfer. So, use those values, use that m, use that b for the stripping section operating line, and exactly solve the same procedure, okay, and then you will get number of plates. You can very easily code this entire derivation in MATLAB or MathCAD, and then that will give you a very handy tool to play with. So, that how does alpha vary, how does the number of plates vary with alpha, with xb, xd. So, this entire algorithm is a very handy tool for optimization of the distillation column. Okay. So, this method is given by Smoker. This is also quite popular method in determination of number of plates. Now, researchers from University of Massachusetts Amherst have further worked on this equation to further simplify it for sharp separation. When xd is close to 1, xd is 0.99 or 0.995, all those things. But you can find these derivations in the book by Douglas, Conceptual Design of Chemical Processes. Right now, I am not covering this because this is outside the scope of this course. Okay. So, now we go ahead. We have now determined, we have seen an important design aspect of distillation column, that is in the determination of number of equilibrium stages. Actual number of plates you can calculate by dividing the theoretical number of plates by the efficiency, that we shall see subsequently. Okay. Now, I told you in the beginning that there are two types of distillation columns. First is the plate column and another is packed column. The decision of selection between these columns depends on various factors. Okay. Decision of column internals must be made on the basis of performance and cost. The options for column internal are tray column, sieve cap, sieve tray, bubble cap tray. Then among packing, there are two types of packing. One is random packing and second is structured packing. Random packings are of various types. I can now I am showing you here on the screen. Rashik rings, then interlock saddle. Rashik rings and interlock saddle made of ceramic. There are two factors. What is the shape of this tower packing and what is the material of construction of this tower packing? Now, in earlier days, ceramic was most widely used because ceramic was very corrosion resistant. Ceramic is essentially an oxide, so it is highly corrosion resistant. So, Rashik rings made of ceramic, interlock saddles made of ceramic, burl saddles or burl rings made of ceramic, then pawl rings made of metal, interlocks metal tower packing known as IMTP, again made of metal, and then cascade mirroring made of metal. Okay. So, these are some of the common tower packings that are used. The tray columns are favored when the operating pressure and liquid flow rate are high and when the column diameter is large. Random packings are recommended when the column diameter is small or problems such as corrosion or foaming are intense. Okay. These columns are also used when batch operations are preferred. Structural packings are considered for low pressure and vacuum operation or for separation of those components where the relative volatility is close to 1. A typical example in this case is the heavy water distillation H2O D2O, where relative volatility is something like 1.005. You get very large number of plates. So, separating this in plate column is practically impossible. So, the structured packing is used, which gives very high interfacial area and therefore, very less height. If you want to find an analogy between number of trays and the packing, there is a quantity called as HETP, height equivalent to theoretical plate, and that we shall see subsequently. Structural packing column give low pressure drop across the column in addition to low liquid hold up. Typically, the tray efficiencies are between 60 to 80% for the sieve trays. Typical examples of random packings I already shown, Rashik rings, interlock saddle, burr saddle, IMTP. Now, there is some discussion regarding the material of construction. The popular material of construction for tower packing is either ceramic or metal, and in the modern days even plastic is being used, but all of these have some advantages and disadvantages. Now, let us see those. Stoneware is susceptible to attack by alkali and acids such as hydrofluoric acid. Metals have issues of wettability of the surface and possibility of high corrosion rates. Plastic packings cannot be used for high temperature operation because they may decompose. The random packings are characterized on the basis of void fraction, surface area per volume, and the quantity which I just defined, height equivalent to theoretical plate. Now, the extent of separation that is achieved in a particular height of packed tower and those between two plates is the analogy between these two. If the two plates of a distillation column give like enrichment in vapor as let us say 2%, then how much height of the random packing is required to achieve the same separation is essentially what is HTP, okay, height equivalent to theoretical plate. The structured packings can provide high mass transfer efficiencies and capacities than the tray column. Due to this, the size of the column required for particular operation decreases. Following general guidelines should be used while making a choice between a plate or a packed tower. First, the stage efficiency of a packed tower is quite sensitive to the type and size of the packing, okay, the fluid rates, the fluid properties, column diameter and operating pressure. So, the manufacturer will report some value of void fraction, some value of operating the pressure drop and some value of HETP, but you will have to conduct your own experiments to verify these values. These values may change from operation to operation, okay, these are not constant. Secondly, if the ratio of liquid mass velocity to gas mass velocity is low, then tray columns are more reliable than packed column due to liquid separation problems in these columns. Then the tray columns can be designed to handle wide range of liquid flow rates without flooding, but that is not possible in case of packed column. If the operation involves liquid with dispersed solids, then use of tray column is more convenient since the plates are more accessible for cleaning. Tray columns are preferred if the interstage cooling is required to remove heat of reaction or solution, as the cooling coils can be installed on the plates. Okay. Another important aspect, tray columns have a liquid pool over each tray. When you have a multi-component distillation, when you want to draw more than 2 products from a column, as we have seen in previous lecture, you can draw 3, 4, 5 products. In that case also tray columns are preferred because the composition on each tray varies. In case where the feed is dominated either by middle distillate or higher heavy component or middle component, then depending on the feed composition you can draw more than one product, and in that case the tray columns are most suitable. Packed tower cannot be used for such purpose. When the large temperature differences are encountered in the column, that means when the boiling points of component differ by large amount, the tray columns are preferred because thermal expansion or contraction of the equipment components can crush the packing. Okay. So, packings are not used when you encounter large temperature differences. And finally, random packed columns are generally not designed with diameters larger than 1.5 meter and diameters of the commercial tray columns are not less than 2/3 of a meter or 0.67 meters. Pack columns are preferred for corrosive fluids and other liquids that have tendency to foam. Why? Reason is very easy. The tower packings can be removed very easily, they can washed, they can be regenerated and put back, but that facility is not possible for trays which are fixed to the column shell. Okay. So, dismantling a plate column and taking off the tower packings from a packed tower are far different things. Okay. So, the latter is always easier, and therefore, whenever you have corrosive fluids or foaming tendency, you would like to go for pack column. Now, we shall see the last topic of today's lecture, that is determination of height and diameter of a sieve tray column. Okay. We are not going to treat pack column because those are not very frequently used. The most frequently used columns are plate columns. Okay. So, the sieve tray columns. The first step in determination of the column diameter is the calculation of net vapor velocity at flooding condition from the expression given by Fair. This was given by J.R. Fair, okay. Okay. And that equation says that VNF, which is the velocity at flooding condition. Now, flooding and loading conditions of a packed tower or any column you have learned in solid fluid operation, also on unit operation. Okay. When does flooding occur? When does loading occur? When there is the gas flow rate is so high that the liquid cannot go out, that is loading point, and flooding point is when the column is filled with liquid. Okay. So, those things are going to be treated in greater detail in other courses of NPTEL. So, I do not go much deeper into it. I suggest that you read through book of Maccabe and Smith to learn about the loading and flooding velocity. Okay. So, the velocity at flooding condition VNF is equal to CSB into sigma by 20 raised to 0.2 into rho L minus rho V divided by rho V raised to 0.5. Now, let us see the notations. CSB is the Souders and Brown factor at flooding condition. Souders and Brown were the first people, first scientists to propose that the flooding occurs due to entrainment of liquid droplets through the rising vapor in a column or rising gas in a column. Okay. So, based on that analysis, they have given this particular expression. That analysis is quite involved, quite complicated. It involves essentially the balance of forces on a liquid droplet. So, when can entrainment occur, under what circumstances it can occur, and so on and so forth. So, that derivation is again out of syllabus. So, we do not cover it. Okay. We take this expression directly, and sigma is the surface tension. Now, sigma by 20, that 20 number is very tricky. If you see surface tensions of most of organic liquids, it is in the range of 20 to 39 centimeter. So, that sigma by 20 factor appears, and then what we have is the ratio of densities rho L minus rho V divided by rho V raised to 0.5. The factor CSB is determined by a chart which is a log plot of CSB against factor L by V into rho L minus rho V divided by half, and the CSB is a function of spacing between the trays. Now, I will show you that chart appears on your screen now. The function CSB, the Souders and Brown factor in meter per second, is plotted against L by V into rho V minus rho L raised to half. L is the molar flow rate of liquid, V is the molar flow rate of mass flow rate. L is the mass flow rate of liquid divided by mass flow rate of vapor into rho V minus rho L. Rho V is the density of vapor, rho L is the density of liquid, and rho V is the density of vapor, and the difference raised to half. And what you have is another factor here, that is the number of the tray spacing. What should be the distance between the two trays? Now, standard spacing between the trays for a large diameter column is typically 0.46 to 0.61 meters. So, let us say approximately 1.5 to 2 feet, but in many situations 0.3 to 0.91 meter spacing is also used, somewhat larger spacing, so that there is enough space to enter the column and clean the column at the time of startup. Okay. The actual vapor velocity Vn is selected by assuming that it is 50 to 90% of the net vapor velocity at the flooding condition, and after determination of this, so CSB you get from that plot for given the surface tension and vapor and liquid densities, and that CSB into this factor sigma by 20 raised to 0.2 and this density ratio raised to 0.5 will give you VNF, and actual vapor velocity Vn is selected assuming that it is 50 to 90% of the net vapor velocity at the flooding condition, and once you select the vapor velocity, then the net column area is An is equal to m dot V divided by Vn, where An is the column area used in the process, Vn is the actual vapor velocity, m dot V is the volumetric flow rate of the vapor. Now, this expression is assumed means this expression is assumes that the entire column area is available for vapor flow rate, but that is not the case. For every plate there is a downcomer through which the liquid will flow. The downcomer will occupy about 20% of the column area, and rest 80% area is available for the vapor flow rate. So, while calculating the net column area, you have to again divide here by 0.8, so that you account for the area for the downcomer. So, after getting the area of the column, you can calculate the diameter of the column in straightforward way. D is equal to 4 into An divided by pi raised to half. So, we have seen as how the diameter of the column is determined. Then comes the height. Okay. Conversion of equilibrium stages to actual stages in the column needs estimation of overall tray efficiency. A few moments before, we saw as how theoretical number of plates can be determined by different methods, whether it is smoker method or FUG method, Fenske, Underwood, Gilliland method, but those are theoretical number of stages. To get the actual number of stages, you have to determine the tray efficiency. Okay. You have learnt an efficiency called as Murphy efficiency in mass transfer operation. A similar efficiency, but is given by Lockett. Murphy efficiency equation is more theoretical, so it is difficult to apply in terms of practical quantities. So, Lockett has given a simpler expression in practical terms for efficiency. E naught is equal to 0.492 into mu L into alpha Lk Hk, that is relative volatility between light key component and heavy key component, average relative volatility. So, E naught is equal to 0.492 into mu L is the liquid viscosity of the mixture, into alpha average raised to minus 0.245. So, dividing the theoretical number of plates n by E naught will give you the actual number of plates, and n actual, that is what we denote n actual. And we already know the plate spacing, because when we calculated VNF, the flooding velocity, we had already decided the plate spacing. The Souders and Brown plot was based on the tray spacing. So, we know tray spacing, and then the height of the column with only trays is obvious, that n actual minus 1 into Hs, where Hs is the spacing between the plates. But the column also has a reboiler and a condenser. The vapors rising from the topmost plate of the column will have lot of liquid droplets entrained in it. So, to remove those droplets, to have the vapor liquid disengagement, you need some extra space over the top plate. That space will also account for any rise in the pressure of the column as the distillation proceeds. So, you have to provide extra space above the top plate. Similarly, you have to provide extra space below the bottom plate, because you have to have a liquid sump that will provide liquid to the reboiler. Why? Because having that reservoir is essential so as to gives some kind of a margin for column operation in case the previous column or the previous supply is disrupted. Okay. So, that instead of feeding directly to the bottom, you need some liquid reservoir. Okay. So, that storage also requires space. Typically, about 15% of the column height is provided as this margin space at top and bottom, and therefore, the total height h is not just n actual minus 1 into h s plus delta h, which is this margin. Delta h is 0.3 into h, 15% of the total height on each side, top and bottom, and therefore, the total height of the column can be approximated as n actual minus 1 into h s, which is the spacing between the plates, divided by 0.7. Remember, there are many approximations and assumptions involved in this expression, but still this gives you a fairly good idea as how tall will be the column for a given separation. Okay. So, today we have seen several aspects of design of a distillation column. First, we compared the packed and plate columns, then we saw what are the steps in design of a distillation column. Then we saw two methods for determination of number of plates in the column, the FUG method, Fenske Underwood Gilliland method and smoker method, and finally, we saw a simple procedure for determination of the column diameter and height. Okay. So, this lecture completes module 4 of our course, that is design of separation processes. In the next two lectures, we shall see several problems on the topics that we have covered in the 4 theory lectures. These topics are essentially the absorber and distillation column design. Thank you.